The invitation to speak at two places at the same time. So I would like to start with a short history of the problem I am speaking about. So I may have some troubles to give proper credits to the first mathematician having worked on that problem. Indeed, there is an old Babylonian clay tablet which is called Plimpton 322, and which is dated back to the 18th century before Christus. And well, if you are not familiar with with this kind of writing, there is a translation. So in fact, you see it's a table. On the second column and third column of this table may be translated as follows. So it's a list of numbers. So most clay tables which were found with numbers are related to, let's say, commercial transactions. But it does not seem to be the case in this particular, for this particular tablet. In fact, there is this various relations between the numbers on the tablet. So if you take the number on the third column at the power 2, and you remove the number on the second column also at power 2, you find out that each time you find a square. So on some of these relations are with quite big numbers, for example the fourth one. And well, such kind of remarkable relations between numbers have fascinated, mankind for centuries. So if you go to the 17th century, but after Deus, then there is the famous problem of Fermat, which is well known, and which was proved, well, much more recently by Waltz, that if P is strictly bigger than 2, then any integral solution of the equation xp plus yp equals to zp satisfies that x, y, z is equal to 0. So there are only trivial solutions to this particular equation. Well, so what is the big difference between p equals to 2 and p strictly bigger than 2? So you can find some easy explanation to explain why there are so many solutions for p equals to 2. So if you look at the equation x2 plus y square plus equals to z square, then obviously you can divide with, you look at solution with x, y, and z integers. Then, of course, you can divide by z square, and then you find a rational solution of the equation x square plus y square is equal to 1. So you look at rational points on the circle. And you know how to parameterize a circle. It's an exercise for any student. So you look at the line going through the point with coordinate -1, 0, and you take the line with the slope t. And this gives another point of intersection with the circle, which is called mt. So this is these equations. And if you look at these equations, then you find out that you may write x and y in terms of t. So this means that if you take a rational number t, then you get rational numbers x and y. Okay, so now let's go back to integral solutions. So I wrote again the formula for rational solutions. If you multiply by 1 plus t squared, well, it turns out that by taking homogeneous formulas for all variables, that you get solutions of the initial equation x squared plus y squared equals to z squared, which is given by u squared minus v squared, 2 times uv, u squared plus v squared, for integers u and v. And in fact, you can prove quite easily that up to permutation of x and y and multiplication of the triples by an integer, you get in that way all the integral solutions of the equation. And in fact, it seems that this way of getting solution was already known by the unknown mathematician of the beginning of the talk, because the various values which were on the tablet are obtained with quite small and simple numbers u and v. So you can easily imagine that the numbers were produced that way. Okay, so let me now go to the number of solutions. So you can be more precise and be interested by how many solutions there are with coordinates which are bounded by some bound b, and you look at it when b goes to infinity. And using the parameterization I gave earlier of the circle, then it turns out that, in fact, it's up to some constant equivalent to the cardinal of the set uv in z square, such that u square plus v square is less than b. So I'm cheating a little bit, but there is a not too difficult reduction to this number. So you see, we started with rational numbers on the circle, and then now we are looking at, in fact, a couple of integers in the disk. And this is very easy to estimate. So I made a drawing for it. So if you know how the area of a domain was defined, well, you see that if you look at the number of uv in z square, such that the sum of u square plus v square is less than b, and you compare it with the area of the disk, then it's bounded by some constant multiplied by the square root of b. Okay, so this says that, well, the number of solutions, so let me maybe go back to the previous slide. So the number which was nb is in fact equivalent to some constant multiplied by b. And I should have said, or rather insisted on the fact that here I'm looking at primitive solutions. Primitive in that case means that I am supposing that the GCD of x, y, z is equal to 1. Since I can multiply any solution by an integer, it gives another solution. That's the point I'm cheating, because to get that the GCD is equal to 1, you have to work a little bit. Okay, so for this equation, x squared plus y squared is equal to z squared, we know that there is about a constant times b primitive solutions. Okay, so is there an heuristic to explain why this should be? So let me try to explain this. So we are looking at the set of x, y, z in Z3, such that the GCD of x, y, z is equal to 1, and the maximum of x, y, z is less than b. And among this set, we want the one for which x squared plus y squared minus z squared is equal to 0. If you look at the cardinal of this set, the cardinal of this set is up to some constant, which can be made explicit. So I should say, well, let's call it m of b. So m of b is equivalent to some constant times bq. So the fact that imposing the condition GCD of xyz equals to 1, in fact, only contributes to a constant, but doesn't change the power of b which is involved. Okay, and now look at the value of x squared plus y squared minus z squared. Well, this belongs to minus b squared 2 times b squared. So if you imagine that integers behave completely erratically, then you think that, well, the number of solutions should be around something times b, which is the case. Which is in fact the case. I gave a sketch of the proof earlier. Now, if I look at higher degree equation, so let's take xd plus yd minus zd. Oh, maybe it's too high on the blackboard. I should wait a little bit lower. Well, with the same type of ideas, well, in fact, these numbers, well, belongs to minus b power d 2 times b power d. So, if d is bigger than 3, the range is much wider. So if integers behave erratically, if you have worked for quite a long time with integers, you really believe that they are completely erratical, then this means that there should be very few solutions of this equation, which is the case. So, okay, now you can think that this reasoning works for any homogeneous equation of degree d. So let's take more generally, I guess. So let's take an arbitrary equation, x, y, z, homogeneous of degree d. And, well, if you think in the same way, well, you think, well, if d is less than 2, then there might be many solutions. If d is bigger than 3, there should not be too many solutions. Well, it's true up to a point. So the idea is that, well, d is the degree of a polynomial is something which is easy to compute with a nice algebraic invariant. You do not need any geometry for it. Well, so there is a nice example which I like, which is Bernoulli-Lemniscate, which is given by the equation I wrote on the blackboard, on the slide. So if you want to take it to make a homogeneous equation out of it, that's fairly easy. Oops, that was better. Another one. No, maybe next one. Oh, that's much better. So, okay, x squared plus y squared square minus, well, I should say plus y squared minus x squared times z squared is equal to 0. So I look at the primitive solution of this equation, which is homogeneous. Okay, so it's the same as looking at the rational equations, rational solutions of the equation which is on the slide. Okay, it turns out that also that the degree of this equation is 4, it's possible to parameterize the solution of this equation in the following way. You look at the circle with the center which is with coordinates t over 2, t over 2, and which goes through the origin. And you look, there is only one intersection of this circle with the lemniscate. Let's call this point empty, and the coordinates of this point empty is given by this formula. So again, you can parameterize the lemniscate with rational functions, which means that, in fact, you can get all rational solutions of the equation in that way. And again, this gives a lot of integral solutions of the equation, which is right here on the whiteboard. Yeah, which is visible now. Okay, so the degree is 4. So what's wrong with this equation? So you can see it on the slide. There is a singularity, which is at the origin. In fact, there are 3 singularities if you think of it in projective terms. There are 1 there and 2 at infinity. So, and by the slide, by the parameterization, I know that in fact it's a rational curve. So it's the same as P1. So since there are many rational points on P1, it's not a surprise that there are many rational points on this curve. It was already in Jean-Pierre's talk. So the right invariant is not the degree. The right invariant is a geometric invariant, and it's the genus. So the genus, we have seen it already in several talks. So what is a genus? Well, I have to consider the corresponding complex curve, which is defined in the projective planes by the same equation. Well, it's a singular complex curve in general, and we consider the genus of C. So if we take a desingularization of the curves, is given as the number of holes in the Riemann surface, as usual. So you have seen already nice drawings in Jean-Pierre's slides. And this genus is a right invariant. More precisely, for curves, the result may be stated as follows. So if the genus is 0, well, this means that on the algebraic closure, so over C, let's say, the curve is birational to P1. Then the number is either 0 or some constant multiplied by, so NF of B is the number of solution of the equation with coordinates of primitive solution of the equation with coordinates which are less than B. Sorry, I skipped that on the previous slide. So, yeah, it was at the bottom. So, NF of B is the number of xyz in Z square, so that the DCD is equal to 1, and the maximum of the coordinates is less than B. So, if the genus is 0, well, the number is either 0 or equivalent to C B over A with some positive, strictly positive real number C. It can be 0. Of course, I didn't give an example where it was 0, but it's easily done. If I take the projective curves with equation x squared plus y squared plus z squared is equal to 0, then the genus of that curve, it's a conic again. So over C, it's isomorphic to P1. So the genus is 0, but it has no solution except 0, 0, 0, which is not primitive. So in that case, the number NFB is 0. So the point is that if it is not 0, then it's some power of B. Okay, if G is equal to 1, well, then we get an elliptic curve, and we have seen already in several talks that this elliptic curve has a group structure. Well, let me draw an elliptic curve. So this group structure, which may be defined over Q, because it is defined also with lines. So if I take 3 points of the curves which are on the same line, then I have the relation P plus Q plus R is equal to 0. So, okay, I have a group structure and I have a way to produce points. So if I have 2 points, I can produce a third. But in fact, if I have 1 point, which is defined over Q, I can define also another one, which is, let's say, minus 2p. So I have, if I repeat this procedure, I have a procedure to produce rational points, as before for the case of the circle, to produce rational points on the curve. So in fact, in that case, the number of primitive integral solutions is either finite, can be finite, or it is equivalent to some constant multiplied by a power of the logarithm of b. Well, the power of the logarithm of b, in fact, turns out to be half an integer. And if g is bigger than 2, then we have Falting's theorem, which was already mentioned in Jean-Pierre's talk, which says that the number of primitive integral solutions is finite. So the behavior is completely given by the genus of the curve. Okay, so now let's go to higher dimension. So what can we say in higher dimension? So once again, I can take some homogeneous polynomial. So I will simply consider hypersurfaces in Pn. That's enough for the talk. So I take some homogeneous polynomial of degree bigger than 2. I should say irreducible. And we are interested in the number of solutions of this equation f of x naught xn is equal to 0. The GCD of the integers is equal to 1, and the maximum of the coordinates is less than b. So what is the behavior of this number nf of b as b goes to infinity? So I can try to do the same heuristics as I have done for the curves, which is still on this blackboard. So let me erase this blackboard. Oh, sorry, this whiteboard. I'm so much used to use blackboards that I forgot the English name for whiteboards. Okay, so, well, the beginning is the same. If I look at all the n plus 1 tuples of integers. Oh, is it visible? Yeah, I should not go higher. So, such that the GCD of x naught xn is equal to 1, and the maximum of the absolute values of the coordinates is less than b, then it's quite easy to show that this cardinal is in fact equivalent to some constant which turns out to be 2 at the power n plus 1 divided by the Riemann zeta function of n plus 1 times b at the power n plus 1. So now I consider the values. So let's take some element x naught xn in this set. Then the value of that polynomial f. So let me remind you that f is a homogeneous of degree d. So this belongs to, well, some minus a times b power d, a times b power d, with, well, for some a, in R. Well, okay, so what can we imagine? Well, we can imagine that if n plus 1 is bigger than d, then the number of solutions, so the number of primitive solutions of the equation f of x naught xn is equal to 0, that is the number nf of b, ought to be equivalent to, well, some constant times b at the power n plus 1 minus d. So this is simply by saying, well, everything should behave in the most erratic way. Well, if this is true, well, then we should have some kind of result like that. It turns out to be almost true. That is, we have a very nice theorem of Birch, which is based on the circle method by Littlewood and Davenport, which is the following. So I need some definition. So if I take any ring, I can look at the solutions with coordinates in this ring. And we say that the solution is primitive if A is generated as an ideal by the value of x naught xn. Okay, so if I take for A field, this means simply that one of the coordinates is not 0. Okay, then assume that n is very big. So very big when compared with the degree. So here the value in the Birch theorem is 2 to the power d times d minus 1. Assume that the complex hypersurface defined by the same equation is smooth. So this is a geometric condition. And assume that there is a primitive solution over R, the field of real numbers, and in Z over mz for any integer m bigger than 2. Then, well, the expected behavior is the real behavior. So everything is as we expected. So I should say, okay, look at these conditions. So the first condition is n is very big. So okay, so that's in fact a limit due to the method which is used to prove this result. Okay, so n very big. Okay. The second one is a geometric condition. I won't spend time on it. Let's look at the other conditions. So if the point is that if there exists a primitive solution in Z at the power n plus 1, then, well, obviously, it gives a solution in R at the power n plus 1, which is non-zero. Then there exists one in R at the power n plus 1. And if I reduce modulo m, well, if the GCD of the coordinates is equal to 1, this implies that when I reduce modulo n, this gives, modulo m, sorry, this gives also a primitive solution. So, 1 in Z over mc for any m. So except for the first two conditions, which is n big enough, V smooth, the rest is satisfied if there is a solution. So in other words, you can translate this by saying, well, either there is no solution, or the behavior is exactly the one expected, which is exactly similar to the thing we have seen for curves of genus 0. So the spirit is that hypersurfaces, smooth hypersurfaces with dimension which is very big when compared with the degree, then this is exactly as curves of genus 0. So it is something you have already seen in the previous talks. So now what does happen when one reduces n? Obviously, this condition n strictly bigger than 2 power d times d minus 1 is not optimal. You see, you could imagine that a similar result is also valid if n plus 1 is strictly bigger than d. So the trichotomy you may expect, I should erase somewhere. Let's erase here. So you should expect three type of behavior, either n plus 1 strictly bigger than d, or n plus 1 is equal to d, or n plus 1 is strictly less than d. Oh, I should write the same n, so it's capital N. Sorry. Well, let's look at an example. So the example I want to look at is one for which we have n plus 1 is equal to d. So I take on rather small dimension. So I should say that the dimension of V over C is equal to n minus 1. And if I take this equals to 2, then for surface, then I get n equal to 3, so the number of variables is 4. Okay, then to have n plus 1 equals to d, I should take the degree to be equal to 4. So the simplest equation you can think of is the equation, which is similar to Fermat equation, x power 4 plus y power 4 plus z power 4 equals t power 4. There are obvious solutions to this equation, simply by taking one for which two of the variables are zero. So there was a conjecture which says that more or less, which was made, I think, by Euler, which was saying that, well, the obvious solutions are the only one, a little bit like Fermat last theorem. Well, it was disproved quite recently by Noam Elkis, who found the following relations between numbers. So, you see, you get rather big solutions of this equation. So this means that, well, you have, well, of course, without a computer it would be quite difficult to find this solution, and even on a computer it's not so easy. So you have to think a little bit before you do the computations, if you do not want to block all the computers in your department. Anyway, so Noam Elkis was able to find these solutions. And, well, in fact, it is now expected, there is a very recent conjecture of well, I attribute it to Van Wyk, which says that, well, let's say for a smooth quartic, which does not contain let's say lines or elliptic curves. So the point is that if the quartic surface contains a line, well, of course it has many points, because there are many points on the line. And similarly, if it contains an elliptic curve, then there is a way to produce rational points simply by looking at the point on the elliptic curve. Then, but in fact I could put here our elliptic curve in parentheses. Let me explain later why. Then, the number of points, of primitive solutions with coordinates bounded by B should be of the form some constant, which is explicit, times the logarithm of B at some power, which is also explicit. So this means that, well, on such a surface, there is no obvious manner to produce rational points. At least up to now, we do not know any simple manner to produce points. But nevertheless, there should be an infinite number of them if, well, this is strictly positive, which is the case in which is in fact always the case. Well, and there I realized that I was too optimistic, so I forgot to if, let's say, there is a solution, then etc. Because you can always imagine you take x4 plus y4 plus z4 plus t4 is equal to 0. Of course, you have no solution except the trivial one. Okay. So now we get some kind of global picture. So yeah, I should have said that in fact my slides will be available at least on my, well, on the website. But I did not write the global picture I'm going to explain now in the notes. So the global picture is somehow the following one. So there was already something which was mentioned in Jean-Pierre's talk. Well, in some sense, the example case is the case when x is hyperbolic. This means for curves that the genus is bigger than 2. So then one expects, so I think it's due to long. So I should say everything is conjectural on this whiteboard. Or almost everything. So x of q should be finite. Let me remind you that this was connected, as well explained in the May's talk, that in particular, this is really an implication in that direction, k of x, which is the maximal exterior product of the dual of the tangent space, should be big on F. So this corresponds also to the case where n plus 1, well, capital N plus 1, is strictly less than d for hypersurface. On the other side, you have the case where, let's say, x fano, or a weaker condition, which is that, so x fano, this means that k of x minus 1, so the opposite to this one, the dual to this one, is ample. But in fact, I think a weaker condition should be enough, so k of x minus 1, let's say big. Then this should correspond to the case where nf of b is equivalent to some constant times b at some power times the logarithm of b at some power. So there are many rational points in that case. In between, well, you have a wide range of examples. In particular, you have this case. You have the case where the canonical line bundle is trivial, which is, for example, the case for abelian varieties, but which is also the case for the example I gave over there. So abelian varieties, smooth quartic surfaces, and so on. Well, here, what is expected is, on the proven subcase, is that the behavior should be n f of b is equivalent to some constant times logarithm of b at some power. But obviously, you can imagine cases which are not on this list, but where, for example, if you take x hyperbolic, then any subvariety satisfies that this is big enough. So this means that you don't have subvarieties which are, for example, lines or birational to projective spaces. But you can imagine varieties for which there are subvarieties which are birational to projective space. So in that case, there won't be rational points everywhere on the variety, but there will be many rational points on the subvariety which is birational to some projective space. So in between, you have all the variety, all the cases where the set of rational points is contained. So the set of rational points, I should have said, sorry, that the set of rational points is the points with coordinates in the field Q of rational numbers. So you have the case where the set of rational points is contained in some subvariety, in some strict subvariety. So maybe. So I should say that for this conjecture of 1 week, in fact, he has computed, there is no case for which it's proven. But there are many cases, he has made many computations on computers, similar to the one done by Noam Elkis, for various kind of quartic surfaces with various rank of the Picard group and so on. And each time, he finds, after removing the lines, that in fact he gets a constant times the logarithm of b at the power, the rank of the Picard group. And it would be very surprising if it was only a coincidence. I really think there is something in that direction. Okay. So what are the limits to that? So up to now it's very optimistic. He said, well, if you know the geometry of the varieties, then you know what happens to the rational points. And so you know about the solutions of Diophantine equations. Well, is it completely true? Well, you can look at the problem in general. So take any family of polynomials with integral coefficients and look at the set of integral solutions. So can you determine if there is a solution? Can you determine if there is an infinite set of solutions, and so on and so on? So the first problem was, in fact, a question of Hilbert's. In his talk in Paris. So it's the 10th problem of Hilbert. And there is a result of Davis, Putnam, Robinson, Matiasiewicz, and more, which says that in fact, so the other people contributed to reduce the number of variables. There is a polynomial f with 12 variables, such that if you look at the map, which goes from z to the set 0, 1, and the value of the function at n is 1 if the equation fn x1 x11 as a solution equals to 0 as a solution, and it's 0 otherwise. So it's simply look whether the solution with the first variable set to n as a solution or not. Well, in fact, this function, which is apparently quite easy to define, well, cannot be computed with an algorithm. There is no algorithm which is able to compute this function in finite time. So I would like to see this result as some kind of Heisenberg principle. You can't know too much about integers. But of course, well, it's only a way to see it. Anyway, so is it the end of it? Well, no, not completely. So there is something on the board saying that I have 10 minutes remaining. So it's not, well, first of all, up to now, I only restricted myself to homogeneous conditions. So homogeneous equations. So the problem of existence of an algorithm for a family of homogeneous polynomial is still completely open. Or similarly, another way to put it is we don't know whether there is an algorithm to determine whether there is a solution with coefficient in Q, which is a very natural question. Over Z, it's not possible by this theorem. Well, is it possible over Q? We don't know. So, well, what can you do waiting for such the answer to such a question? Well, you can look at easier example. So maybe it will take some time for the drawing to come up. Okay. So you can look at example for which, in fact, we are in this case we are for it's a we have the anti-canonical line bundle which is big. So this is a case with many rational points, and you can try to compute the number of rational points with bounded size on this surface. So I draw the surface. I draw also on the picture. I hope you can see at least the green dots. So green dots are rational points. On the other side, there are blue dots, which are also rational points with bounded height. So in fact, obviously by the equation y squared plus z squared is equal to some polynomial in x, you see that there are fibers which are circle. So it's a circle, we know. It's isomorphic to P1, so there are many rational points. And in fact, you can show quite easily that there are an infinite number of circles with the rational points on the surface. So this means that there are a lot of points. You know already that there are a lot of points. But you have to prove the precise estimate. And well, it's a quite recent result with de la Bretèche and Timberling that in fact the number of points on that surface is the expected one. Okay, so I should mention maybe about the colors of the points. Why are there green points and blue points? It's not to test whether your view is very good. It's because green points and blue points are determined depending on depending on the condition modulo a power of 2. So the computers decide the color of the point looking at the coordinates of the point modulo some power of 2. And depending on the reduction modulo this power of 2 of the point, it decides whether it's green or blue. And you may see that, in fact, all the blue points are on real component of the surface, and all the green ones are on the other component. So you see, before I said that integers behave completely erratically. Well, this is not completely true. It's not completely true because in that case, in fact, there is some relation between a condition which is purely modulo a power of 2 and the real condition. But I won't go into that since apparently if I want to leave some time for the questions, I have to stop here.
Questions? Well, we don't have questions right now, Emmanuel. Thanks a lot.
So there is a question by Benoit Kluckner.
In the Davis-Putnam-Robson-Tiasevich theorem, what is the degree of the polynomial?
It's big. I don't remember exactly what
okay,
the yeah, I'm not completely sure that they really produce the polynomial itself. I will have to check that. I'm not completely sure. They give a procedure to find it.
Okay, because then you have the choice between a polynomial with few variables on high degree or few degree on many variables.
Yes, exactly. Well, it's related to this problem of producing polynomials such that each positive value of the polynomial in several variables. Each positive value of the polynomial is a prime number. It's related to that. Any more questions? Yes, Roland?
The generating series, enumerating the number of solutions according to B and putting this into a generating series.
Yes.
Are there cases where one can say something?
Yes, in very simple case. Well, what you look at is rather the corresponding zeta function. So you may look, well, let's write it in that way. Zeta of f of s to be the sum for the solution. So f of x naught xn is equal to 0, and of the well, let's say GCD of x naught xn is equal to 1 over the maximum of the absolute value at the power s. So this is this converge for s real part of s big enough. And then you can look at this zeta function, height zeta function. Well, you can prove properties, but not so nice as Riemann zeta functions. For example, in general, it's not possible to have a meromorphic continuation of this function to the whole complex plane. So in particular, you cannot expect to have a functional equation. Any more questions on both sides?
Pas de question.
There is a question by Philippe. No?
Standard question is, what about the constants? Can you tell us something about these constants?
Okay.
Well, maybe.
So I can give you some indication for this particular conjecture.
Okay.
For this particular conjecture, it's, in fact, I should have said it. Thank you very much for this question. So you see, in that case, the canonical line model is trivial. What does it mean? It means that, in fact, there is a volume form on the variety. So there is a section, global section, which gives a volume form. So I will go quite fast at this point, but...
Attention, la conférence se termine dans 2 minutes.
Sorry, so I have 2 minutes to finish. Afterwards, I can go to see the new French movie, Rio ne répond plus. Because so anyway, so you have this value form, and the constant is a product over all places, so I should say all prime numbers, of the volume, so I'm going a little bit faster, of the point over QP times the volume of the point over R. So the point is that, well, this volume form is defined up to a constant, but if you look at this product of the volumes, it does not depend on the choice of the section. So this is entirely canonical, and this is a constant which comes here.
And the exponent?
So the exponent is the rank of the Picard. So, but you have first to remove the elliptic curves on lines which are contained in the surface. 1 minute remaining, so you have to be very fast if you have another question.
On peut continuer, on va essayer de les taper en direct, si vous voulez. Pierre?
Oui. Là, je vois le tableau.
Do you wish to continue, or do you have enough of me?
No, I mean, we will be. I mean, the connection will be closed. So I mean, so sorry because we cannot do anything about that. This is the at the IN2P3 that they will just close the connection. So anyway, let me just maybe we can go on discussing if you want to. So let me just thank you again, all the three of you. Okay, and bye bye before they just cut the line. Bye bye.